Okay, off we go. So, gonna finish up the course material. So, here we go. Last time we finished section 4.1, on to 4.2. Okay, I do need everybody to settle down, please. Again, I know it's challenging. I know that y'all want to talk about the exam, but we really got to cover material here. Okay, so 4.2, here's the good news. It's super, super similar to single variable optimization, like ridiculously similar. So in particular, here's three conditions that if they hold, such as they do at a point like this, we can guarantee that there's no way that that's at the maximum value of the function because the function is still increasing, and therefore this is definitely not a maximizer. It's a very simple little argument, right? If the function is still increasing, you're not at the maximum, right? So very simple. And so the way we actually enact this is we sort of turn it around and say, look, if any one of the above conditions fails, any one of the above conditions fails, then our process of elimination fails, right? If we can't make a case for why it's not a maximizer, it might be a maximizer, right? So we call them critical points, and then we check the values later, by whatever method. Okay. All right. It's the same thing in multivariable, like the same thing. Here is a list of three conditions, right? If you're in the middle, if you're in the interior of your domain, and if the function's differentiable and you have a non-zero gradient, that non-zero gradient is pointing in the direction in which the function is increasing, which means, again, you're not at the maximum yet. You're still going up, right? So again, no way that could be a maximizer. It's just not possible. Doesn't make any sense. The function's still increasing. Okay, so again, with that argument in mind, we have to confess that if any one of these conditions fails, any one of them, right? If any one of those conditions fails, in other words, if any one of these things happens, right, then we can't. It's possible it might be a max. I can't eliminate it, so I have to confess. Who knows? Maybe that is a maximizer. And again, we call it a critical point, and we check the values later. Okay. All right. Easy example. Here's a function. It's defined on all of R2. So let's go through the process. Are there any boundary points? What's the boundary of R2? Well, there isn't any. So no boundary critical points. Where does this function fail to be differentiable? Nowhere. It's a polynomial. It's differentiable everywhere. So no what we call differentiability critical points. Right? And then lastly, take the derivative, set it equal to 0. Where is the gradient equal to 0? Well, okay, now here we have to do a little bit of algebra. Good news in this case, it's easy algebra. It's pretty immediate to see that y has to be 0 because of that equation. Right? And pretty easy to see that because of this, we must have x being plus or minus 1. So boom, there's our two critical points. Right. Very similar to single variable calculus. Practically the same thing. Okay, now sometimes the algebra gets a little hairier. I arranged for a really easy first example that we just looked at, but now this is not a gradient, but hypothetically, if it were, and if we found ourselves solving this system, which is this would not be unrepresentative of the kind of thing you might see. You can't just you can't look at one equation and solve for one variable. This is kind of mixed, right? There's x's and y's in both equations. So what do? And in this case, by the way, all of this kind of stuff is by hook or by crook. There is no sort of single, this will always work kind of process. In this case, this equation tells us that x squared is y squared, which has two possible breakdowns, right? X is either y or it's negative y. Which one? I don't know. And now, so we have two different cases to consider. And we consider this case. And then secondly, afterwards, we would have to consider this case. Right? It's just algebra. Y'all can do those separate cases. The big point that I want to warn y'all about on this one is don't forget that you do have to consider both cases, right? So many students make the following mistake. Again, it's a tragic error to see, but so many students seem to think that if x squared is y squared, then that means that x is y, and they just kind of forget about this little annoying second possibility, right? Well, that's a real problem, right? So first of all, it's not mathematically valid reasoning. And again, that's what we do here, right? This is math class. Mathematical reasoning is what we're here for. So that's the first problem. But now, I mean, just from a results point of view, notice this critical point down here you would miss, right? If all you did is look at this one case, you would only get these two critical points, and you would miss that critical point. Not to suggest that the punchline, the bottom line of your work is what matters. Certainly not. Again, it's the reasoning, right? But even from that shallower point of view, it's still wrong. Okay. All right. So do be careful about cases. The second derivative test, again, it's also very similar to single variable calculus. If you look at Taylor polynomials, why does the second derivative, why is that the player in the second derivative test in single variable? Well, because everything else in this term is positive, and so that second derivative decides whether this second order term is always positive or always negative. It all comes down to looking at the second derivative. If you look at the multivariable Taylor polynomial, remember we talked about that last time. What determines if this is always positive or always negative, or possibly neither? Well, it's a harder construction, right? It's not a product of three scalar factors. There's a dot product. These are vectors and matrices, and there's different operations, matrix, vector, multiplication, dot products. It is harder to tell. In fact, again, reminder, you may recognize this is a quadratic form. Okay? Quadratic forms are a non-trivial bit of linear algebra. And whether this is positive definite, negative definite, or neither, and thus which one of these outcomes is determined by rules that y'all probably remember. At least you remember that they existed back in linear algebra. So now you can streamline those. There's a very cool little bit of linear algebra. If you're in the market, if you want to, test, how well do you remember your, linear algebra, this is highly optional, right? You don't have to do this, right? But if you want to see if you can connect those dots, and it's a little non-trivial, this hits the highlights. Take a look if you're interested. But here's what you can do, if you want to streamline it, here's the punchline. This is the second derivative test as applied to functions of two variables. It gets a little weirder if you have more than two variables. We're just going to do two variables. And notice, it's a little flow chart. Follow the flow chart, right? You are going to need to look at the Hessian determinant. So, compute the Hessian determinant. You're going to need to look at, wrong color. You're going to need to look at one of the unmixed partials. Fxx is arbitrary. You can use Fyy if you prefer, but arbitrarily Fxx. Follow the rules, follow the flow chart. It will answer the question to the best of its ability. Do notice, however, that it is possible that the test might fail. Well, again, same as in single variable. Okay. And this example is as straight up just doing that test. Very readable. Y'all can read this yourselves. Notice that I compute the Hessian determinant. Right there. Notice that I pick out in particular Fxx, which of course is right there. Right. It's the first top left element in the matrix of second partials. And again, just look and see when's it positive, when's it negative. Follow the rules. Boom. Okay. All right. Okay. This stuff about global extrema is a pretty easy read, at least this stuff at the beginning. Give it a look. It's not really something we're going to focus on. Again, time is tight, etc. So I'm not going to spend time talking about this in class, but give it a quick look. And again, don't forget, y'all have got the recordings from my other class in which I go through all of this in pretty good detail. You've got my recordings from past semesters. If you want to see the details, go ahead. This example is basically a incentive. The fact that this works out so poorly is hopefully incentive to take the next thing we're going to talk about more seriously, which is a much better method for how to deal with boundaries. And that's what I'm going to go to right now. Again, so the point of this example is how much it stinks to consider boundaries when you don't have Lagrange multipliers. So I think that's pretty easy at a glance to see, yeah, that looks pretty unappetizing, doesn't it? It looks like a lot of effort with square roots and pluses and minuses and single variable calculus. It looks kind of annoying. Okay, and it is. All right, so here's the good stuff. Lagrange multipliers, very powerful idea. It addresses what we call constrained optimization. So we want to, there's some function we want to maximize or minimize, could go either way, but you can't just consider any point you want. There's some arbitrary external constraint that you have to satisfy. Okay. So for example, a classic example would be something like this right here. So we want to find the point that's closest to the origin. Seems like that'd be a pretty easy question to answer. Point closest to the origin? How about the origin? Right? Easy question. Problem solved. Nope. There's a constraint here. We only want to look at points that are on this curve. This, what is that? Curve. By the way, it's an ellipse, but whatever. The origin is not an allowed candidate. So now we have a hard problem, right? Looking just among points that satisfy that equation. Now, how do we optimize? Not clear. Okay. All right. So, the method, Lagrange multipliers method, requires breaking down the question in a very specific way. So you have to do the following. First, find what it is you want to optimize. Well, in this case, we want to minimize, right? But in general, it could be minimize or maximize. So distance to the origin. It's what we call our objective function. Now you're going to notice that formula I wrote down is not distance. That's distance squared. A quick appeal. I think it's pretty satisfying if I claim that I've found the point that minimizes distance. I have also found the point that minimizes distance squared. And vice versa. I mean, it's just a quick thought, right? I mean, if you make distance squared as small as possible, then you've also found a point that makes distance as small as possible. So it's a clever idea. It avoids having to deal with square roots, and so slick move. So that's what I'm going to call the objective function. That's what we're going to try to minimize here. The second thing you have to do, there's a little hiccup on this. You have to express your constraint as a level set. Very important. It's got to be a level set. You'll see why in a couple minutes. You've got to rewrite your constraint as a level set. Level set of what function? In this case, this is the function whose level set gives us our constraint. So this is what we're going to call our constraint function. So whenever you have a constrained optimization problem, if you want to use Lagrange multipliers, which you do, it's awesome, right? It's a really powerful method. You got to identify what is your objective function. You got to identify what's your constraint function. Okay, so real quick, a couple more examples of, again, how to just set this up. Let's look at these two examples down here. These two examples down here. What is it that we're trying to optimize? If you want to find the biggest volume, then it's a volume that you're trying to optimize. If you want to maximize productivity, okay, well then productivity is your objective function. Okay, what is it that we're looking at a level set of to define our constraint? Well, here we have a given fixed amount of area. In the next example, we have a limited, namely fixed, budget. So area and budget are our constraint functions. So the purpose of this, aside from spending more time making clear what these functions are, notice how routine and relevant, right? I don't have to go to some great lengths to create some scenario where I would need a constrained optimization method. These are very routine, very practical kinds of questions that we need answers to of this, things like this, right? And so this method, I'm trying to make the pitch, is something that you're going to be using one way or another regularly. Okay. All right. How does this work? The big idea, again, is a process of elimination. Here we have a list of 3 conditions that, if they happen, mean that my constraint gradient is pointing perpendicular to the constraint set, and my objective gradient, by not being a multiple of the non-zero constraint gradient, has to be pointing off axis, right? They're not parallel. That means that it will have a non-zero shadow projection, you might call it, down in the tangent plane, and that means that I can compute the directional derivative. I get a dot product that's got an acute angle in it. That means it's definitely positive. That means the function is still increasing. And if it's still increasing, you're not at the maximum yet. It's still getting bigger. So, again, we eliminate most of the points in our constraint set by this elimination argument. So, with that in mind, again, just like in single variable, we're going to look now for points where one or the other of these conditions fails. And this is what it would look like if one of those conditions fails. We look for failures of differentiability. We look for where the constraint gradient is 0. By the way, that's for reasons that we can't talk about in this class, that's called degeneracy, for really good reasons. But anyway, that's terminology as far as we're concerned. And then there's this condition right here. We call this the Lagrange condition. This is usually the one that will yield the actual critical points, but keep in mind, that's coincidental. To have a complete argument, you have to check all 3 conditions. And they're called critical points, and then we check them later. Okay, so examples to follow. Right? Now again, we're short on time, so I'm going to cut to the quick of what the most important points in these examples is. There is a little bit of a flashback to linear algebra. Make sure you're good with that. We're going to think it through. Remember how non-singular matrices work and their connection to non-zero determinants and existence and uniqueness of solutions and all of that business, right? So make sure you're good with that. Keeping in mind that we're looking to eliminate possibilities. If you come up with your algebra with a point that it's not even a candidate in the first place, you don't need to eliminate it, right? The whole purpose of our elimination process is to eliminate things that might be what we're looking for. If we already know it's not what we're looking for, don't waste your time with it. So x equals 0, not a critical point. The other thing that I want to point out is that this algebra that results is sometimes kind of hairy, right? Here's the 4 equations with 4 unknowns that you get when you write down the gradient equation and the constraint. And this is what we have to solve. This algebra can be tricky. And this algebra sometimes has sneaky little bits that you have to worry about. So, for example, very tempting to look at these 2 equations and cancel the lambdas, and then you get nice, handy little relationships between x, y, and z that make everything fall apart. How do you know you can cancel a lambda? What if lambda is 0? You need to establish that lambda is non-zero, and this right here is how you know that lambda can't be 0. So please don't sweep stuff like that under the rug. Make sure to look at these remaining examples. I think they're really convenient. See y'all later. Have a good one.